especially on Friday, you have 4 hours, 4 hours, and hold by 2 TMs. So do not waste the good chance to do that. Right? And yeah. So let us continue with the decision trees. In the last lecture, we introduced the definition of decision trees, right? The basic concept of that. So in a nutshell, decision tree is a hierarchical structure that represents data. Right? The creation of decision tree can be viewed as a recursive partitioning procedure of the whole data set. Right? So, for example, from this set of data, right, those instances are colored shapes, right? We can pick up the attributes in some particular order to create the tree, and each node in the tree represents a subset of data. So obviously, the root node represents the entire set of data, but then each node is associated with some feature to do the split, right? And then for each node, we're coming out several branches, where each branch corresponds to one testing condition. That is, the associated feature takes a particular value. By using that test condition, we can take out a subset of examples from the current set of trained data, right? So then we'll do it recursively until we arrive at a subset of examples which have a unique label. Then we should stop because it's not necessary to split anymore. Then we'll create a leaf node and then use the shared label of all the examples on the current data set as label for that leaf node. Right? So we have manually created such a tree. We first pick up the color, and then we split the data set according to like 3 possible color values, right? Blue, red, and green, and then we do it recursively until we reach all those leaf nodes. Right? So when we finish the tree creation, right, how can we use this tree to make a prediction for a new example? Right? Say, if I have a new example which is right triangle, right? How can we predict the label of right triangle? So basically, we can start with the root, right? And then to find out the path from the root to the leaf, then we use the label on the leaf as our prediction, right? Take the right triangle as an example. I'm going to first look at the root node, so the test feature is colored. And then, because it's red, so I'm going to go through this branch, right? And then I thought, okay, I have a red leaf. Then I report the label on this leaf, right, which is B. That's our prediction. Okay. So in general, to make a prediction for new example, I just start from the root node and go through the test features, and according to the values of each test feature take, you will find a path from root to the leaf, and finally, you report the label on the leaf. So it's pretty convenient. But I also mentioned an embarrassing case, right? So for this tree, we created manually. When we present the tree, say a green triangle, what's the problem? Doesn't have a rule. Yeah, we cannot predict it. Well, why? Because green triangle, okay, green here, and shape we found, okay, there's no branch that the shape can take triangle. So stuck here. So this is not allowed in practice. No matter how simple your tree is, you must provide a prediction for arbitrary labels, for arbitrary instances. Right? So we're going to talk about how to address this issue from decision tree learning algorithms. So those are just some review of decision tree concept. Right? So we also mentioned that.
Excellent. How can we decide about attributes? Which attribute we have to set it upper level?
Yeah, that's a very good question. That's the main task we're going to address today. Okay. Any other question?
What was his question? Sorry.
He's mentioning that how can we select? How can organize the order of the attributes to split the data recursively. Namely, which attribute should be placed in top level, which one should be in intermediate level, or which one should be at the bottom level, right? This is a very important question, actually. If you want to implement decision tree learning algorithm, you must address this problem. Any other question? Okay, so so I also mentioned that essentially decision tree can be viewed as a conjunction of set of rules. Why? Because from the tree root to each leaf node, there's a path, right? This path essentially is a rule to make decision, make the prediction decision, right? So just enumerate all the paths, you get a set of rules, you conjunct them together. This is another way to represent your decision trees. So this is quite intuitive because that resembles how human brain learn a concept or predict the label for some object, right? So come out set of rules and say, okay, whether this kind of rule is satisfied, then I can make prediction. So from the example, we say, okay, the outputs are just discrete categories, right? So same as intuitive, right? But what if my labels are continuous? Can we still do decision tree? The answer is yes, but we need to change a little bit the stopping criteria. From our manual example, when we stopped growing the tree, we found, okay, the current node contains a purely labeled example. I mean, all the examples have the same label. Then we stop. We use the current node as a leaf node, right? But if our labels are continuous, meaning we're doing regression, you cannot assume that every example has the same numerical value. Right? It's not possible. Right? But we can still do the regression tree. But we just need to specify when to stop growing the tree. We create a leaf node. And then, of course, the leaf node might contain multiple training examples. Then how can we output the label, the continuous label? Mm-hmm.
You could do a range rather than just like a single value for the output.
Yeah, that's one solution, right? That's one solution. Sounds good. Is there any other solution? I'll give the most, simplest solution, the most stupid solution. I'm going to take average of all the labels. That's it. Of course, you can choose to provide a set of continuous labels. That's fine. Right? But even easier, you can just take an average and say, okay, just report this numerical label. And this kind of tree is called regression trees because your task is regression, right? You're going to predict. You're going to give the continuous prediction. And also, in practice, the data are filled with noises, and you often see the cases that your label might be incorrect, or corrupted by some noises, or your features are missing. Some kind of features missing, right? And to construct a robust decision trees, we need extra tricks to address those issues, which we'll cover later, right? Like how do you prompt the structure of the trees, and that will help with noise. And how do you complete the missing attributes, right? Or incorporate the missing attributes into the computational ranking of the features to do the splitting. That's something we'll discuss later. Yeah. So, and also from our example to create decision trees, we say the instances are represented by attribute value pairs, right? So like those values or the values for those attributes or features are all categorical. Like you have blue shapes, you have green shapes, you have red shapes, right? Blue, green, red. You have rectangle shapes, you have triangle shapes, blue, rectangle, triangle, circles, right? But what if you have continuous features? You have numerical features like length, or like height, like temperature, like price. How can we deal with that in the tree construction?
You have like preset bins or ranges?
Yes, exactly. Right? That's the way we often use to pre-process the continuous features. We're going to first discretize or binning the trees into different regions, right? Then we just test whether the feature value falls in, say, region 1, region 2, region 3, until region n, right? Or even simpler, I can set up one single threshold, right? Then I just test whether the feature value is below the threshold or bigger than the threshold. In this way, your numerical features is turning into categorical features or binary features. And with that, you can continue to expand your trees. So discretize them or use thresholds on the numerical values. So I'll show you the example, right? So this is our training set. Well, you have two continuous features, x and y. So I'm gonna discretize both x feature and y feature into 3 regions for each. So you can see the combination of the discretization actually partition the whole feature space into different rectangle regions, right? And then our continuous feature x is converted into categorical features, which 3 possible cases, right? So x less than 1, x is between 1 and 3, x is bigger than 3, right? And for y is bigger than 7, y is between 5 and 7, y is less than or equal to 5, right? And based on that, we can construct our decision tree for these continuous features, right? So here's the tree construction. You can verify manually. So you can take a look. Just follow one branch, right? So to say which specific region the decision tree represents, right? So suppose let us look at whether x is less than 3, right? Suppose this is no, that means okay, x is bigger than or equal to 3. So I'm gonna look at this part, right? X is bigger than or equal to 3, right? And then we arrive at this node, and then we're gonna test whether y is bigger than 7, right? So x is bigger than or equal to 3 represents this region, and further we test if y is bigger than 7, so it arrives at this region, right? So we have one single positive example, so it arrives at a leaf node, you end up with a positive label. Right? But if y is bigger than 7 is false, that means okay, y is less than or equal to 7, you actually arrive at this region, right? X is bigger than or equal to 3, and y is less than or equal to 7, right? So I have two negative labels. Right? Both the examples are labeled as negative. So arrive at leaf node, the label is negative, right? Now similarly, you have other branches as well. So when we mentioned that decision tree is very intuitive, means just a conjunction of set of rules, right? But it does not mean it's very simple. Actually, decision trees can represent very complicated models for prediction, say classification or regression. How do we say this point, right? If you look at the decision boundary of this decision tree, what is decision boundary? Decision boundary just means, okay, the boundary which separates the positive examples and negative examples. It looks like this, right? So it is a highly nonlinear decision boundary. So actually, decision trees can be more flexible or complicated than many linear models, like linear regression. Because you'll see, like linear regression models, the boundary, or linear classification models, the boundary is just a line. Just to give you the impression that decision trees are intuitive but not very simple. It can represent very complicated models. Any questions so far? Okay, good. So we have introduced the general definition of decision trees, and so basically we can view decision trees as a compact data representation, right? And also a natural representation. Why is natural representation? Because the hierarchical structure resembles like human beings thinking of problems. Like if you want to take survey, you answer 20 questions, you arrive at different conclusions, right? It's very similar to human learning behavior. Actually, later we'll discuss. We'll briefly gossip the history of decision trees. We found they originated from psychology research. That psychology research is telling you about like how human beings start to learn concepts. So, and predicting with the decision tree is pretty straightforward. Why? Because we're just starting from the root and test each feature and follow the branches where the test condition is satisfied, and finally, if you end up with the leaf node, you report the leaf node. Right? And this question is important. Clearly, given the data set, there are many decision trees that can represent. Right? Some students have asked this question in the last lecture. Right? So take the shapes, the color shapes as example. Like we create our tree with first using color, right, and then use shapes, right? So if we reverse order, we first use shape to split data and then use color, you'll end up with totally different decision trees. Then that brings in an important question: which tree should be the best? If I want to build an automatic algorithm, right, I want to construct the tree from data automatically, I must specify an order. And this order turns out to give you some like optimal results, right? But be optimal in what? That's the focus of our lecture today. Right? So. Oh, I have, yeah. So that's some actual exercise, right? The same data. I encourage you guys to create the decision tree manually by using shape first and then color, and you can compare with different tree structures, and you can look at like for the same test instance, will the two trees give the same prediction or not? So next we're gonna.
Sorry, I have a question. So we have more features like the number of shapes in each figure. So we add more features, not just the color and the shape, but the number of shapes. That can be another feature.
Yeah, of course.
And how do you decide like how many features you want to extract?
That's the feature processing procedure, right? But in our case, I mean, for this simple practice problem, you just assume you have two features, right? But in practice, you have to decide which features you want to incorporate. Numerical, categorical, Bloom features, whatever. But actually, the feature set you decide to incorporate into your learning task is important. This feature extraction procedure, right? We mentioned in the last lecture. Right? Okay, so next we'll talk about the details to learn decision trees out of our data, right? So we're gonna introduce the classical algorithms called ID3 algorithm to learn decision trees, namely automatically create decision trees from data. So you will see that this is essentially a greedy heuristic algorithm to choose features each time, to choose the best feature each time to split data, and then recursively split data accordingly until you reach the leaf nodes. And this algorithm was proposed by the pioneer in decision tree research. His name is called Queenan. And after we introduce the algorithm to learn decision trees, ID3 algorithm, we'll introduce some extensions of that. Okay. So before the illustration of algorithm, here's the brief history of decision tree research. So full search decision tree methods to model human concept learning. So at 1960s. So as I just said, right, decision tree originates from the study in psychology. Those scientists want to know, okay, how human beings are learning concepts, right? That's why they design decision trees. So that's why I say, okay, decision tree is quite intuitive. It's kind of consistent with our humans' ways to learn to predict something, right? And then in late 1970s, Queenan developed the classical ID3 algorithm, which uses the information gain heuristics to learn, well, the decision trees from examples. Well, why it's called expert system? Because in 1970s, late 1970s to 1980s, expert system is buzzwords. It's just like artificial intelligence nowadays or machine learning in nowadays. So basically, you can see them, you can build them as like equivalent. And then ID3 is kind of a very fundamental algorithm because all kinds of variants of decision trees are based on ID3. That's why we focus on ID3. Right? And then later, those are statisticians, right? So they developed the CART algorithm. So it's called classification regression trees based on ID3. So as we mentioned, regression trees can predict continuous label. And then a variety of improvements for decision tree learning were proposed in the 1980s, coping with noises, continuous attributes, and how to deal with missing data, etc. And then in early 1990s, Quinlan updated his decision tree learning algorithm to C4.5 and C5. So if you want to use decision tree to address your practical problems or your research problem, if you do not want to implement from scratch, I would suggest you to download the package C4.5, C5.0. I'm not sure whether C4.5.0 is free. Because Quinlan has a company. His company sells the decision tree packages. If you're interested, you can take a look at the web page of his company. Yeah. And then later, people find that decision tree can be a very good base learner for a set of ensemble learning algorithms, namely boosting and bagging. So this is a topic we will cover after decision trees. So the idea is simply like you integrate a bunch of very simple decision trees and combine their prediction to make the final prediction. And turns out the performance can improve dramatically. So that's the brief history of decision tree research. Right? So nowadays, decision trees can become some kind of standard benchmark algorithms, and in many applications, it's already being used. So to illustrate the decision tree learning algorithm, to better illustrate it, we'll walk through a specific supervised learning task. So the task is to predict whether I'm going to play tennis outside, given today's weather. Right? So how do we characterize the weather conditions today? We're going to use 4 features: outlook, temperature, humidity, and wind. So all 4 features are categorical. So outlook features has 3 possible values: sun, overcast, and rain. Temperature has 3 possible values: hot, mild, and cool. And humidity has 3 levels: high, normal, low. And wind can be strong and weak. And our label space only contains 2 labels, right? Positive and negative. Positive means that, okay, I'm going to play tennis outside. Negative means, okay, I'm going to stay at home and watch movies or episodes, whatever. Okay, so this is a problem setting, right? We use this as an example, right? So, and also, we assume that we have collected a set of training examples. We have 14 training examples, which records on the 14 different weather conditions my decisions to play tennis outside or not, right? So here for brevity, we use the first letter capital to represent those features and their values, right? Overcast O represent overlook, and S sunny, O overcast, R raining. Temperature T hot, H medium, M C cool, humidity H high, N normal, L low, and wind W strong, S strong, W weak. So we're gonna use our ID3 algorithm to recursively build the decision tree in a top-down fashion. So this is the result tree. You see that when you run your ID3 algorithm on this data set, it will first select the feature outlook to split data. And you end up with like 3 subsets, right? And for the sunny days, right? we further use humidity as feature to expand the tree. Then you end up 2 leaves. For overcast examples, you'll see that all the examples have the same label, so positive label. So end up with leaf node. And for the rain examples, we're going to further choose wind feature to further split data set and expand the tree. You end up with 2 other leaves. So now let us look at the algorithm framework which end up with this tree. So here's ID3, right? So first, ID3 is a recursive algorithm. What does a recursive algorithm mean? It means that it will recursively call itself to create new tree nodes for the partition of current set examples and new branches. I assume everybody has at least heard of recursive programming, right? If you have taken data structure and algorithm design course, you shouldn't feel strange of that, right? So the input of ID3 algorithm has 3 elements. First, S is a set of current examples, right? So S may represent, okay, the entire examples, or may represent the current subset examples corresponding to some tree node. So be aware of that, because when you call ID3, it could be in the intermediate step to expand the tree on the existing node, or you start from scratch, right? And the second input is label, namely the target attribute or feature I'm going to predict. Like in our tennis playing case, the label is just my decision, right? I'm going to play outside positive. I'm going to stay at home negative, right? And third input will be the attribute set. So from which set of attributes I'm going to select one feature to further split the current set of examples S. So is everybody clear about the input? Okay, great. So whenever we develop or design a recursive algorithm, what's the first step?
Decide your base case.
Yeah, base case. I mean, yeah, exactly. Yeah. You want to say something? Oh, sorry, I misunderstand your gesture. Okay, so let me give a more detailed explanation. It said that we need to decide base case. What does base case mean? It means the stopping criteria. Like in which basic cases I'm gonna stop. Otherwise, you can imagine like recursive algorithm will keep calling itself, right? If you do not stop, or if you have like an ill-defined stopping criteria, it just keep calling itself until it consumes all the stack space and kill the program itself, right? So you must specify in what kind of cases you stop growing. You end up with, in our decision tree, construction means that you end up with leaf nodes, right? And then you in what kind of situations should we stop growing a tree and end up with leaf nodes? Can anybody give me some hint on that?
Perhaps after you've examined every attribute, right?
Yeah, examine every attribute and then?
Well, at that point, you have to arrive at a decision or a label.
Yeah, you have the right decision label, right? But then, how do we make decision whether I'm gonna split the data or not? Probably. That's fine. That's totally fine. Any other idea?
Maybe once like your set of examples all have the same label, you can like stop that.
Yeah.
And,
yeah, exactly right. That's our manual stopping criteria, right? Any other ideas on that? Yeah, you're right. First, when your current examples, all examples have the same label, it's not necessary for us to further split data, right? We should stop and return a leaf and use the unique label as our leaf nodes label, right? But there's some starting point here you need to be aware as well. If the current set of attributes are empty, we have to stop as well, right? Why? Because we always need an attribute for the split data, right? But now I don't have any attribute to select to split data. I have no choice. I have to stop, right? So our stopping criteria actually consists of two cases. First, if all the examples in S have the same label, we do not need to split data, so we stop, create new nodes, we just return leaf node with the current label, right? And second stopping criteria is that, okay, well, my labels might still like mixed, but I don't have extra features to do the split. My attributes set are just empty. That have to stop, right? Then the question is that which label should we use as the label for the leaf node? And here we're going to use the leaf node with the most common label, right? So suppose I have like 50 examples, right? But I don't have any attributes to split 50 examples. And in these 50 examples, like 30 are positive and 20 are negative. Then I'm going to report the leaf node has positive label, right? Does this sound reasonable? Okay. So those are the base cases, right? So if we haven't met these base cases, right? That means we can still create new tree branches and create new nodes on that, right? How can we do that? Otherwise, right? Otherwise, we're going to first create a root node for the current tree. The root node means a root node for a subtree. If you run the algorithm from scratch, okay, the root node will be the whole root node, right? But if you call this algorithm again intermediately, then it will create a root node for a subtree, from which we're going to further expand branches and nodes, right? So once we create a root node for the tree, and then we're going to go through each attribute in the current set of attributes. Then we will select one attribute, say A, that best splits the data set. So one may ask, what do you mean by best splits the data set, right? So let us just hold off this problem, right? Let's just look at the algorithm procedure, and then we'll come back to look at how do we best split the data set. So suppose when we go through all the attributes in the attribute set and find someone which best splits S, then we're going to use this particular attribute to split data, namely S, right? So how can we do that? We just enumerate all possible value V that the selected feature A can take, right? And then we can pick up all the examples that belongs to S, whose feature A takes the value V, right? We can denote this subset of samples as SV, right? Obviously, for SV, we're gonna add a new tree branch which corresponds to A equals to V, right? So it's just like, okay, along this branch A equals to V, I'm gonna pick up all the subset examples with A equals to V. We denote it by SV. Okay. Any question at this point? So the same as we manually create the decision tree, right? We use we pick up a feature A, and then we look at, okay, how many distinct features, feature values that A can take. For each distinct value, I'm gonna pick up the corresponding examples, and then I create a branch, right? So now let us look at SV, right? What if SV is empty? Namely, in the current set of examples S, no examples whose attribute A takes value B. And what should we do?
Could you just continue the loop and just move on to the next value that the A can take?
Yeah, that's one strategy, right? But there could be some problem with that. So let me tell you the solution first. Right? So I'm gonna, even SV is empty, I'm gonna add a leaf node. and leaf node will use the most common label in S. So why should we bother to add actual leaf node on that? You got it, right?
Yeah, that's the exact example we ran into before with like the
green
I think
triangle.
it's the red triangle.
Yes, that's the motivation, right? So if you look at the tree we previously created by our hand, you say, okay, when you partition the data, you look at all the green shapes, right? You say, okay, there are green circles, there are green squares, there's no green triangles, right? So we leave, okay, we miss one branch, right? And then there comes a embarrassing case. Right? If you want to test what's the label for green triangle, you end up with nothing, right? So now, with the setting of ID3 algorithm, even at this step, right? At this step, even when I look at the green shapes where there are no triangles, I'm intentionally add one more branch, right? And a leaf node on that, and I'm gonna choose the most common label from this subset examples as the label for this leaf node, right? And for this subset examples, it corresponds to all green instances, right? For all green instances, we'll have like 2 label B instances and 2 label A instances. The most common could be B or could be A. You can choose either of them. Does it make sense? Any question? Yeah. That's why we should add this one small operation on that. Is to ensure that no matter what kind of weird test cases appear, your decision tree can always report a label on that. But if SV is not empty, that means, okay, I still have a subset of examples in S such that its attribute A takes the value B, then what should we do next? What should we do next?
Call ID3, passing in the subset samples
Yes.
and the attributes remaining.
Yes, that's where we do the recursive calling, right? Because I'm gonna tend to try to recursive SV again, right? To create new nodes and new branches, right? Yeah, and then below this branch and add a new subtree created by ID3, right? So when we call this ID3 recursively, obviously the current subset of examples will be SV, right? The subset of examples in S such that A takes value B, right? At the same time, be aware we need to remove attribute A from current feature set to perform split. Why?
Well, if you've already split it up by color, splitting it up by color again is meaningless because since it's already been split by that, say you have everything that's red, you can't split it again into red, green, and blue.
Yes.
So it's pointless to test something like that.
Yes, exactly. Exactly, right? Because you have already used A to split the data set, right? I mean, each subset, like SV, its examples will share the same value of A, right? So if you use A to split again, you split nothing, right? That means you have to remove the feature A from attributes. And then you recursively call ID3, and probably you arrive at leaf nodes, or probably you can further to the split. And again, you create all the branches of trees, and you arrive at all the leaf nodes, you return. You have a question?
Oh yeah, just to clarify on the if there on number 3, is that supposed to be the most common value of label in S sub V, like with that specific attribute, or is it just the most common label in the entirety of the set of examples?
That's a very good question. Here I offer you a choice that the most common value of label in S, right? But in some cases, people choose to use the most common label in the entire set. It depends on your choice.
Okay.
But ideally, I mean, if S has reasonable large size, right, you're gonna still use the most common label in S. Why? Because you haven't finished all the other tests. I mean, if your current examples arrive at the node, which represent S, right? So actually you have to go through all the other tests. You should be better, you should be more accurately classified by the most common label in S. But in some cases, if S is very small, like only 3 or 4, and then that kind of most common label might not be statistically reliable, right? And I might jump back to the upper leaf, or even to the upper node to pick up the most common, or even jump back, or even to the root. Does it make sense?
I see.
Yeah, but that's related to like different variants of ID3.
I apologize if we already covered this, but for number 2, find attributes with best splits. Best splits just means divides the data the most.
No.
No. What is meant by best?
Yeah, that's something we're coming right now.
Okay.
Yeah.
Okay.
That's very important, right? If you do not know how to best split the data set, well, you cannot implement this algorithm, even giving you this nice looking pseudocode, right?
Yeah.
So now, to explain what do we mean like by best split data set, right? So let us look at what is the goal, right? If you want to learn or construct a decision tree to represent data, right? Obviously, we know, okay, different orders of features to split data will end up with different structure of decision trees, right? Different width, different width, and different depth, right? So now I want to ask, suppose you are able to enumerate all possible trees that represent data, right? So which tree would you like best? Which one do you think is best? The largest one or the smallest one?
One with the least number of branches.
Yeah, that's
smallest one.
Why smallest one?
Less, shortest time to the leaf nodes.
Oh yeah, that's the important insight here. Any other comments? Intuitively, we might think, okay, the smaller tree is better, right? But in general, I want to put it in a more general principle. It's called Occam's razor principle. So it's a very widely used principle, or even like philosophy in scientific and engineering domain. So what does Occam's razor principle mean? So in general, it says, okay, if I have observed some phenomenon, say the running of Earth is surrounding the sun, right? I want to explain it, right? So I come out a bunch of models or algorithms, whatever. Right? So each model can well explain this phenomenon. But each different models have different complexity. See, model 1, it just incorporates like 2 mathematical formulas to explain everything, right? To explain why the object looks like an ellipsis, right, rather than the right circle, right? And model 2 might have 10 mathematical formulas, and model 3 might have 1 million mathematical formulas. Right? So now, if you are the scientist, right, which model do you believe more, or which model of choice do you want to make? The smaller one. That's called Occam's razor principle. So basically, okay, if I have a set of theories or models can explain the same phenomenon, I'll always pick up the simplest one. In other words, do not increase complexity when it is not necessary. This is called Occam's razor principle. Well, I'm not saying this is some kind of ground truth. It's just some philosophy, some kind of scientific principle. We make the choices, but it's very widely used. In machine learning, it just means, okay, if I have a set of training examples of data, right? I have a bunch of models. Each model can well fit the training data. Then I'm going to choose the simplest model. And we'll give some further analysis of what. Right? So actually, if you use complicated models, very complicated models, it will tend to overfit data. If it tends to overfit data, it will be heavy. It will be very sensitive to the data noises, which are common in practice, and leads to a very bad generalization performance. So we'll come to that point later. But here, I just want to tell you what is Occam's razor principle. according to Occam's Recursive principle, among all the possible tree structures, each of tree can well represent data, right? I will pick up the smallest tree. Does it make sense? Right. Then the issue is that how can we pick up the smallest tree, right? How can we pick up the best tree according to Occam's Recursive principle? Right? Obviously, I mean the most straightforward method is to enumerate all possible trees, right? But this is a combinatorial problem. Right? You have n features, you have like n factorial possible combinations, right? And then do the trees. We don't have enough time and energy to do that. Right? So that's not a practical way. It turns out that finding the minimum distance trees consistent with data is pretty hard. And then in practice, how can we arrive at some small enough trees in a very efficient way? That's the idea of our ID3, right? Greedy search. If you look at the algorithm framework of ID3, right, we never like going back to enumerate features, right? Each time we make the optimal choice, which feature is the best, and then split data. And next time I fix previous features, right? I fix all the previous selected attributes, and then from the remaining attributes, I pick up the best one. So this is a typical greedy algorithm, right? So what is greedy algorithm means that, okay, I just make the best option under current context, namely locally, right? And then I fix the current choice and I move to the next step until we finish everything, right? So, but local optimality does not always lead to a global optimality. Right? But benefit is that even it is not global optimal trees, it ends up with some small trees close to global optimal. That's sufficient, right? Because as long as it's small enough, you see like the performance is really good. Right? But we can get these small trees in a pretty quick way, right? Very efficient way. That's the idea for this ID3 algorithm. So the recursive algorithm is essentially a greedy heuristic tree. Search for some simple tree, but cannot guarantee the global optimality. Because each choice, each time I just pick up the current best feature. It does not consider the long-term effect. So the main decision in our ID3 algorithm is the selection of the next attribute which best split data, right? So hopefully this procedure can help you better understand, the essence of this ID3 algorithm. It's just a greedy algorithm to construct a small tree. So now, the problem becomes, we haven't solved the problem. What does it mean for best splitting the data, right? But if you are the algorithm developer, right? I want to come out a greedy algorithm to construct a tree to be as small as possible. What kind of feature selection principle I'm going to use? An idea? Mm-hmm.
You always probably want to try to split the number of elements in half every time. That makes sense.
Okay. That's the way you control the number of examples, right? So that you can, it's just like balanced trees, like a data structure that you might end up with some on average small trees, right? Yeah, that's pretty interesting, right?
This might be too general, but you want the distance from the main root, the longest distance from the main root to a leaf to be the shortest possible number of edges.
Yeah, that's one way. But you need to come up with some detailed strategy to arrive at that point, right? I guess.
Maybe split on the feature with the least positive variance.
Least positive variance.
Yeah.
Okay, that's one way of doing that. But what if I, have multi-cons labels? Then probably you choose the we just split the example with the smallest number of classes or labels. Yeah, that's fine. This is good brainstorm. Any other idea? Yeah. Okay.
I was saying something similar about correlation, like the one with the highest correlation between two categories.
That is possible. That's possible. Okay. That's sure.
Try picking the attributes that divide the sample space into the most categories, so that the overall size of the remaining, or of the subspaces that it creates are smaller, but it makes a wider tree.
Oh, okay. Okay. Yeah, that's another option. You have.
Yeah, it's prioritizing any attribute that leads directly to a label.
You mean unique label?
And yeah.
Yeah. That's definitely a good choice, right?
Do we know how much the many algorithms use apart from optimality? I mean, for example, 2-factor approximation or something like that.
No, actually, it's not. There might be some analysis on that, but it is actually very quite wide.
Maybe like the attribute where like the subgroup belonging to that attribute has like the least number of observations. Like you can compute like what are the next two attributes off the split on, and then split on those like the smallest number of attributes like at the next branch below.
Yeah. I think that's feasible as well. Yeah. So we can come out a lot of heuristics, right? So this is very good brainstorming. But let us look at how ID3 choose the heuristic. Namely, what's the best feature according to ID3's perspective, right? So to explain that point, so let us look at an example. So suppose I have a data set with two balloon attributes, buying features, A and B, right? So here's the distribution of the examples. So when both A and B is 0, we have 50 negative examples. When A is 0, B equals to 1, we have 50 negative examples. When A is 1, B is 0, we have no examples. And when both A and B is 1, we have 100 positive examples. Right? So then the question is that which attribute would you like to choose to first split data set? An idea?
You want to do whether A is 1 or 0?
Yeah. We can do that on hand, right? If you choose A to split data set, okay, you will end up with two subsets. Each subset is purely labeled, right? If A is 1, it means that, okay, I have 100 positive examples because there's no negative examples here, right? And so A is 0, we have 100 negative examples. So that's it. Right? But if we use B to split the data set first, we don't get purely labeled nodes, right? Because when B is 0, of course, when B is 0, we have 50 here and here, right? We have 50 negative examples. But when B is 1, we have like 50 negative examples, 100 positive examples. We have to use A to split again, right? So obviously, using A is better than using B, right? Now, if we change suppose we add 3 more examples. That means for the case that when A is 1 and B is 0, we have 3 negative examples. Now I want to say which attribute should be selected to split first. Right? Again, we can do it manually. So if we use A to do the split first, so we end up with 2 subsets, right? When A is negative, we have 100. We still have like 100. When A is 0, we still have 100 negative examples, right? But when A is 1, we have 100 positive examples and 3 negative examples, right? And when we split the data set with B, right, we end up with two subsets. The first subset is that 53 negative examples, which correspond here and here. When B is 1, we still have like 50 negative examples and 100 positive examples. So now, intuitively, which attribute do you like better? Still A, right? Why?
Evenly balanced.
Evenly balanced.
The margin is more clear.
The margin is more clear. Right. So let me state your thoughts. I sense your idea. I think we are on the same page. But let me state it in another way. So actually, why we would like to prefer A? Because after using A to split, your subset you get is purer than using B, right? You use A to split, okay. Although I have still have mixed examples, but most of them are 100 positive examples. Only a few of them are 3 negative examples, right? But if you use B, okay, it's more, let's mention that, more even balanced. So it's much less pure than using A, right? So now comes out our heuristics. So we want to find out a feature, the best feature, that after using that feature to split data, the splitted subsets are purest than using other features. So you can imagine that if every time I choose the feature that split data into the purest data set, you can imagine after very few steps, I can arrive at the subsets which all have unique labels, right? That's the idea of the greedy heuristics, right? So every time I choose the feature that can end up with a subset which has the highest purity. Then you can expect that, okay, after a very small number of steps, you'll reach the leaf node. Leaf node means that all the subsets are purely enough, right? Are totally pure, unique labels. And then, because you only take a few steps, you can expect the tree is small enough. Does it make sense? Then the next question is that, we need a way to quantify the purity, right? How do we measure the purity after split data sets, right? So now let us look at the whole strategy again, right? So to keep it in mind, right? Our goal for decision tree construction, we want to have the resulting decision tree as small as possible, and we cannot enumerate all possible tree structures, so we have to choose some greedy heuristic method. Our idea is that we want to select the attribute that split instances that are relatively pure in one label. That means, okay, after I split data sets, the splitted subsets get purer and purer, right? We want the feature that end up with the largest improvement in purity. That feature we will it as the best feature. Then we use that feature to select. And then we recursively call this algorithm on the splitted data subset each. Then we use this heuristic to select. And we'll expect that because every time I obtain the largest improvement in purity, we can use a very small number of steps to arrive at all the subsets with unique labels, namely leaves. Then we end up with small trees, right? Does it make sense? Purity means okay. This is purer than this, right? But later we'll give the mathematical definition of purity.
The probability of you getting the right answer is more than.
That's one way to measure it, right? But intuitively, don't you think like this subset is purer than this subset, right? It's very intuitive, right? But the problem is that, okay, we need some mathematical metric to quantify them and rank the features, right? I'll pick up the top one.
So purity is like
they're like the two different outcomes of the both split between. Does that make sense?
Yes, yes. Yeah. But we need some metric to evaluate that. All we discussed so far is kind of like intuitive, right? So naturally, we feel, okay, the subset data set splitted by A is purer than those data sets splitted by B. And then we need some metric to rank all those features according to the improvement of purity.
Is this just variance?
All variance is one way to do that. And we will use information gain to measure the purity improvement, which is based on the concept called entropy. So how many of you have heard of entropy? Okay, so entropy comes from a information theory. Of course, some physics area talk about entropy as well, right? So, but entropy basically means a measurement of the uncertainty. So, suppose you have a set of examples, right, which are labeled as positive and negative, but I want to measure how uncertain I'm about the labels in examples. Say, I blindly pick up example in your set, right? So how sure I'm about the label of that example? The measurement of whether I'm sure or unsure about the label is called entropy. So you can imagine that if my set of examples are purely labeled, like just one label, then I can pick up any example I say, oh, it's positive label. That means I don't have any uncertainty about labels in your example, right? That means when your data set are pure, the purest, then your uncertainty is the smallest, right? On the other hand, if your examples are totally, half positive, half negative, right? Now you random pick up one. You want to say how uncertain you're about the example, right? You are most uncertain about that. I can even know which label appears to be in more chance, right? That means I have the largest uncertainty. At the same time, my purity is the worst because it's half-half mixed, right? So we use entropy to indicate the purity. Right? So the larger the entropy, the smaller the purity. But what's the definition of entropy? So the entropy is defined as follows. Right? So if you have only like a binary label of examples, it is defined as minus p plus logarithm p plus subtracted p minus logarithm p minus. Right? So here p plus is a proportion of positive examples, and p minus is a proportion of negative examples. Right? In general, if we have k possible labels in our data set, so we have k probabilities, right? P1, P2 to Pk. Each of Pk represents the proportion of label k in your data set. Then your entropy is defined as this summation over k possible labels, where each summon is minus pi logarithm pi. So this is the standard definition of entropy. So what kind of properties does the entropy reflect, right? So if all the examples belong to the same label, entropy is 0. Take the binary label as well, right? As an example, if all the examples have the positive label, so we know that p plus is 1, right? So 1 times log 1 is simply 0, right? But here is 0 log 0, right? So 0 log 0, of course, is not valid. It can directly evaluate. But here, when we take p minus is 0, we are talking about the limited case. So namely, when p minus approaches to 0, what's the limit of this p minus logarithm p minus? The limit is 0. That's how we define this term. So we can use you can verify this. I use L'Hopital's rule or laws to do that. Right? It's in calculus 1. You can show it's pretty straightforward to show that the limit when p minus approaches to 1, this p minus log p minus approaches 0. So then in total it means that if all the examples belong to the same label, the entropy is simply 0, meaning that you have the 0 uncertainty. Meanwhile, you have the largest purity, right? And it also can show that if p plus equals to p minus equals to 0.5, your entropy arrives at maximum, which is 1. Then your purity is the smallest value. So from the information theory, the coding theory, entropy can be viewed as number of bits that are required on average to encode the distinct labels. Right? If the probability of positive is 0.5, then you have to use single bit to code the label 1 and 0. But if it is 0.8, that means it is skewed distribution. On average, it can use less than 1 bit. So just some result from coding theory. If you're interested, we can take a look at some information theory book. So we can take a look at how entropy varies along with P plus and P minus. So we see that when P plus and P minus are equal, namely 0.5, your entropy arrives largest. 1 means that you are most uncertain about the labels of examples in your data set. At the same time means that, okay, you have the smallest purity, right? Because your examples are mixed so uniformly. But if you have a skewed proportional proportion, say P plus is much bigger than P minus, or P minus is is all in between, you will say the entropy is much smaller, right? That means, okay, your purity increases a lot as compared with this case. Any question regarding the definition of entropy? Okay. So in the general case, suppose we have like k possible labels, right? K categorical labels, and we can prove that if the labels follow a uniform distribution, then the entropy of your data set is the highest, meaning that the purity of the data set is the worst, because all kinds of labels are uniform mixed, right? Here's the visualization of that. If all the labels distribute uniformly, you will say this is the entropy. The largest uncertainty means that the worst purity. But if you have like a skewed distribution of those different labels, you can increase the entropy a lot. So now let me summarize, right? So we can calculate the entropy for any label training set, right, or data set. And the high entropy indicates that your uncertainty is high. At the same time means that your purity is bad, right? And a low entropy means that, okay, you're very certain about the labels of examples. That means, okay, you have a little or no uncertainty, and then your purity is good, right? The best case is that, okay, you have 0 entropy, meaning that all the examples have the same label, then your purity reaches the best. Now, based on purity, based on the definition of the entropy, which can evaluate purity, we use the so-called information gain. We calculate the information gain to evaluate, after you split the feature, what's the improvement of the purity. Remember, our heuristic is that we want to select feature that best improve the purity after splitting, right? So how can we reflect the improvement of the purity? We calculate so-called information gain. So what is the information gain? Defined as follows, right? So to calculate what's the information gain for a specific attribute A, to split the data set S, I'm going to first calculate the entropy of the entire data set S. Then I use A to split data sets into several subsets, right? And for each subset, I can compute its entropy. Then I do a weighted average of this entropy according to the size of each subset. Then I subtract the entropy of the entire set S by this expected entropy of the feature splitting. This is called information gain. So you can see that it actually computes the average reduction of entropy, right? So when entropy increases, purity increases, right? So the reduction of entropy is actually the increase of purity. Does it make sense? Is everyone really comfortable with this definition? And any question regarding this?
How do you calculate the entropy of S?
Use the definition here. You're gonna look at.
Just count the outcomes and divide it by the total number of outcomes.
Yeah, you need to look at the proportion of each labels.
Okay.
Yeah. We'll look at some concrete example for the information gain. Okay.
So you're looking at like the number of features in each subset, and then like kind of weighting it by its entropy and summing them.
Yes. And then for each feature, you're gonna calculate such kind of information gain, which actually measure the improvement or increase of purity after splitting, right? And then I will pick up the feature who can obtain the largest information gain. I will use that to split this.
So basically, whichever attribute reduces the amount of entropy the most is the best fit for the root.
Yes. Remember, entropy represents uncertainty. The larger the entropy, the larger the uncertainty. That means the smaller or the worse the purity, right? So decrease of entropy means increase of purity, right? So information gain actually measures the increase of the purity. So I want to find out a feature which increases purity best. Okay. So there's something you should be aware that when we calculate expected entropy, we should weight the entropy of each split subset according to the size of the data. Why? Because it's reasonable. Consider that you have, when you use feature A to split the data set, right? You have one subset which contains 100 examples. You have another subset only contains one example. Well, if I have only one example, the purity is the largest, right? Because you only have one unique label, right? But obviously, the purity of these 100 examples are much more important than the purity of this one single example, right? So we need to weight their importance according to the size of data. Does it make sense? Okay, great. So now, let us use information gain to select features to construct our decision trees for this supervised learning task, right? So we start to create our root node, right? To create our root node, we need to select features all from this 4 feature. Right? We need to decide which feature is to be used to partition the data first, right? So to do that, we need to compute the information gain for each feature, all temperature, humidity, and wind. Right? So let us take a look at all, right? Before we compute the information gain, we need to compute the entropy of the entire data set, right? So now the entire data set is just this 14 training examples, right? So because it's binary labels, so we need to calculate the proportion of each label, right? So P is proportion of positive labels. So we can say there are 9 positive examples out of 14 total examples. So proportion of positive examples, P, is 9 over 14, right? So proportion of negative examples is 5 over 14. And based on that, we can compute the entropy of the entire data set using this positive ratio and negative ratio. So minus positive ratio multiplied with logarithm positive ratio subtracted by negative ratio multiplying with the logarithm negative ratio. So it is approximately 0.94. Just take the second digit, right? And next, I'm going to look at the first feature. I want to evaluate the information gain for the first feature to split data, namely outlook, right? So if we use outlook can take 3 possible values, right? So we'll look at the 3 subsets, use distinct outlook to obtain, right? So first, when outlook is summing, we have 1, 2, 3, 4, 5 examples, right? So all the 5 examples has outlook value to be sunny. So all of these 5 examples, we can see that we have 2 positive examples. Why? This one and this one, right? And the remaining 3 are negative. So that means the positive ratio of this subset is 2 over 5, right? And negative is 3 over 5. And then we can apply the formula to compute the entropy for this subset, where the outlook is sunny, which is 0.971, right? But this is just one subset, where the outlook value takes sunny, right? Outlook has 3 distinct values, so we need to look into the other 2 subsets. The second attribute value that outlook takes is overcast, right? So when the days are cloudy, we say, okay, there are 4 examples. Right? So here, number 3, outlook is overcast. Third, outlook overcast. And 12, outlook is overcast, right? And 13, outlook is overcast. So you can see 3 positive, right? Example 7 positive, right? And example 12 positive. Example 13 positive. So all the examples are positive. What's the entropy? 0, right? You don't need to apply the formula, just 0. So now let us look at the last subset obtained by using outlook split, right? That is when outlook is raining. Right? You see that there are only 5 examples, and there are 3 positive examples out of these 5 examples. So the negative ratio is 2.5, and I calculate the entropy again 0.971. Right? So now we have entropy for each subset using outlook to split, where each subset takes different outlook value, right? So now we do the weighted average according to the size of the data. Okay? So the first subset where outlook is sunny has entropy 0.971, and its size is 5, right? And so it's weighted by 5 over the total number of examples is 5 over 14, right? And second one, entropy 0, so it doesn't matter which way it multiplies to, right? And third one also take 5 examples, so the weight is 5 over 14, multiplying with its entropy. So we get the expected entropy to be 0.9694, right? And finally, we subtract the entropy of the entire subset by the expected entropy, you end up with the information gain, which is 0.246. Now I got information gain for all, right? So apply a similar procedure to evaluate the information gain for humidity. Right? So for humidity is high, we have 7 examples, where 3 of them are positive and 4 of them are negative. So hopefully you guys after class can verify it by yourself, right? And you can calculate entropy, which is 0.985. And for humidity is normal, you have 6 examples, or you have 7 examples as well, and 6 of them are normal, 6 of them are positive, and only 1 negative. So the entropy is 0.592, right? But for humidity equals to low, there's no examples. See, there's no examples for humidity equals to 0. So you don't need to calculate that entropy for the empty set. So now you calculate expected entropy weighted by the size, right? 7 for humidity high, 7 for humidity normal, and you end up with expected entropy to be 0.7885. Now we calculate the information gain, subtract the entire data set's entropy by the expected entropy 0.1515. So now I got information gain for humidity.
Is it possible if you had really random data that information gain would be negative for all of your categories?
No, information gain
will
will
be positive for one of the categories.
Yeah, that's you will see the problem in the coming homework asks you to prove that.
Oh, okay.
That should be a bonus problem for undergrad and then obligatory for grad students.
Okay.
Yeah.
Thank you.
Right. So similarly, we can compute the information gain for wind feature and temperature feature. So now we can rank all the features according to their information gain, right? So now, which feature do we choose to split data? Outlook, right? Outlook has the largest information gain, So we split our outlook. So now, when we use outlook and split data, because outlook can take 3 possible values, so I have 3 subsets, right? So see that, okay, when outlook takes overcast, all the 4 examples are positive. So here we simply arrive at leaf node, right? And report positive label as the node, as the leaf node's label. So we need to look at the other 2 subsets, the sunny examples and rain examples. So what should we do? Again, we apply the same procedure on each of these subsets. Right? So this subset, is 5 examples correspond to the sunny examples. So we have like 2 positive examples, 3 negative examples. And now we're gonna select features from the remaining 3 attributes: temperature, humidity, wind. So you can see why we should exclude outlook, because all the outlook values for these 5 examples are sunny. It's not meaningful to use outlook features to split data again. Right? That's why we should every time exclude the features that are already used for data splitting. And apply the same procedure. You're gonna choose humidity as the best feature to split data. You end up with 2 leaf nodes. That means each subset are purely labeled. But here is the subtle point. Before you leave, just think for a while, for 30 seconds on that. What's the subtle point here? What's the subtle operation we need to do here?
Do you need to put a low branch as well?
Yes, exactly, right? Remember, humidity can take 3 values, but in our data set, there's no examples whose humidity is low, right? But you cannot forget it, otherwise you could miss some embarrassing case later, right? So in this case, we need to put actual branch where the humidity is low. At this time, because we don't have actual examples where the humidity is low, we need to look at which label is the most common in the sunny examples, right? So negative example is the most common. So we'll report the label of this leaf node as no. Similar procedure applies to raining examples. We will choose the wind as the best feature to split, and you end up with 2 leaf nodes as well. So now we'll finish the construction of the whole tree.
And you don't have to like recalculate the entropy of like the subset, right? Because you did that earlier.
Yes, exactly. That's a good.
Just like
that's
keep that running.
Yeah, that's a good trick to avoid recalculation. Right? Or otherwise, you even do not calculate entropy. You just compare the negative expected entropy, right? Because they're constant, plus or minus the expected entropy. But this is just computation trick. It's different conceptual. It's not a conceptualization. Right? I want to give you a concept of information game. Okay, so a brief summary. Our ID3 algorithm to learn decision trees is essentially a greedy heuristic. The base case is that if all instances have the same label, create a leaf node with that label. Another case is that if the attribute set are empty, we have to stop, right? And otherwise, find the best attribute and split data for different values for that attribute. Here we use information game as our heuristic to select the best attribute. And then recursive on the split data set. So now we'll finish the introduction of the ID3. In the next lecture, we'll discuss several variants, say other criteria than information game. Actually, we can come up with other ways to measure accuracy as well. Okay, see you on the next one.